Recording's rolling. It is Monday, March 24th. Yeah, welcome back from spring break. Hope you guys had a good break. No, I did. Breaks are always nice. So, remind you guys where we are. We've been going through review. So here's the review we did leading up to spring break. Right, and then I haven't seen you guys in a week. And then here's the review we have to do. And then there's still a few AP classroom practice exams we're going to do, and that'll take us to the AP exam in May. All right, so here I'll go over this with you guys. Oh, right. So Unit 1 by AP's book. So I'm going by AP's book. They did update this a few months ago. So Unit 1 is kinematic motion. You guys remember these three kinematic formulas I always have on hand? You guys remember those? And where do you apply those? Well, there's linear motion and there's projectiles. So 1 dimension and 2 dimensions. Okay. There's also, you guys remember X versus T, V versus T, A versus T graphs? Right? And these are all related to each other. So if you have information for one graph, you can kind of figure out what the other two look like. For example, guys, if V versus T is linear, X versus T is a what shape? Parabola. And A versus T could be a constant, like a flat line straight across. Okay, so Unit 2. Now, last year, this used to be 2 different units. They shoved it all into one giant unit. We got Newton's laws of motion. You guys remember Newton's laws? Deal with like forces, free body diagrams. I wrote over to the side here. I'm supposed to. You guys remember springs? Like the force in a spring. It's called Hooke's law. F equals kx. I think. There's also circular motion. You guys remember turntables? There was some kind of inward acting force to hold something in a circle called centripetal force. You guys remember? What's a formula for centripetal force? mv squared over r. Yeah, F equals mv squared over r. It can be provided by tension, it can be provided by normal force, it can be provided by gravitational force, which might lead to an orbit, like that. Okay. There's also the turntable version of this one. It goes m times omega squared times r. Okay, guys remember that? Okay. Universal gravitation. You guys remember F equals gmm over r squared. You can get gravity fields from that, like gm over r squared. Right? You know, the mass and radial size of a planet. There's a good chance you're going to see some questions about like what if there's some planet X that's like 3 times the radial size of Earth and 7 times the mass. You might figure out what's the gravity field at the surface. Orbits. Can you guys derive a circular orbit from scratch, or I should say orbital speed? Right? Can you derive orbital speed from scratch for a circular orbit? I think we did that a couple days before spring break. Right, so clear your notes there. Right. All right, so that's what we've done so far. Right, and then take spring break. All right. What we got to do in the next week or two? I'll just however this paces out. So here's what to look forward to. So the rest of the class. So today we're going to do some energy and power. You guys have a packet on your desk. It's that 3-page energy packet. Do I have a? Well, okay. I'll dig up one here in a minute. Okay. So that's going to be your main focus today. Then. Later on, probably towards the end of this week, we'll get to momentum and collisions. You guys remember if objects are colliding, you have to consider that momentum is conserved. Guys, momentum, is that a vector or a scalar? That's a vector. So if 2 objects are traveling the opposite direction, they sort of subtract momentum from each other, right? That's one thing that means, right? Impulse, you guys remember, it's a change in momentum. So if you're focused on a single object, it could change its momentum. Okay. But if it's a closed system, guys, is momentum conserved in a closed system? Yeah. So the impulse for a closed system will always be 0. Okay. But if you're looking at a single object, say if some object's being rammed into, right? How about a force versus time graph, the area under that curve? Okay. And then now units 5 and 6. Now last year, AP used to treat this all as one giant unit, but they split this into 2 smaller ones. This is rotational dynamics. So they did also throw rotational kinematics in here. So this is like turntable physics. So how far is the turntable turned? That's theta. How fast is it rotating? That's omega. And if it's speeding up or slowing down rotating, that's alpha, right? Angular acceleration. You could connect these back to if you put a coin on the edge and watch it move, like how far is it moved in a distance way. Right? Guys, how do you figure out how far it's moved? Is that theta times r? Right, guys, right, so, right there, torque. You guys remember using a wrench, opening a door, R cross F. If there's a net torque, it's going to result in an angular acceleration. Here's Newton's second law of motion, but in rotational form. It doesn't say F equals ma. It says torque equals I times alpha. Right, power equals I alpha. Okay. And then unit 6. So here's the other half of rotational dynamics section. Okay, unit 6. We got. Oh, guys, what does capital L stand for in this class? Angular momentum. Okay, so put a little arrow vector, vector arrow. That's I times omega, rotational inertia times angular velocity, kind of analogous to P equals mv. Okay. There's also kinetic energy of rotating. So K equals 1/2 I omega squared. This is the energy associated with rotation. This can help you quickly solve like what is the like how fast is the volume while moving at the end of an incline. If it's rolled down an incline, you could use this. Okay. Unit 7 is your harmonic motion, simple harmonic motion, and there's really two categories of puzzles you'll see. You tend to see pendulums and also blocks on springs, right? All sliding back and forth. Sometimes you see an oddball question, like if there's an ice cube in a glass of water and it's bouncing up and down, that sort of fits in there too. Okay. But it's usually either pendulums or blocks on springs. And then finally, unit 8 was fluids, and fluid dynamics. So I have 4 ideas here. They're all a little bit different from each other. Archimedes principle, right? So what's the value of a buoyant force? There's Pascal's principle. So pressure is transmitted undiminished. You can set up hydraulic lift with that. Conservation of flow. So if you have a pipe system where the diameter of the pipe is changing throughout the system, the flow rate is conserved. Okay. And then that leads to Bernoulli principle, which tells you how the pressure changes throughout that system, right? So there it is. There's the whole course at a glance. Right. So you guys good so far? Very good. All right. All right. So before I go on, you guys know, of course, we're going to be doing this energy table today. Right before I hit that, one more thing is my other class. I'm moving on to electricity. So I'll flash some electricity stuff up here real fast, just for a few minutes. Right. You guys see a Van de Graaff set up back there? If you guys get an opportunity the next couple of days, if you want to shock yourselves on the Van de Graaff, that's always fun. It's built with a static charge. So it's some kind of static charge. This is a unit that okay. Like a few years ago, if you were in this class about 5-6 years ago, AP used to ask about circuits. So I'll probably take a few days in the future to teach you guys about circuits, but first be real fast because not on your AP exam. Okay. But if you had a current flowing that's and measured in amps, a battery like a AA battery has 1.5 volts potential difference. It's sort of like a pressure trying to push electricity through. There's some resistance in ohms, and then power in watts. Now you guys do know power in watts because that's like a rate of energy. Okay. Right. Here's a breakdown of what those units are, and some extra ones down here. Okay. We're working with electric field. So if you turn on the Van de Graaff generator and one of those bulbs is like charged up, right? You can feel that. Maybe a little shock there. Okay. You have 2 charges. They can attract or repel. Now these 2 I got opposite charges. Guys, do opposite charges attract together?
Yes.
Right. And look at that. It looks just like universal gravitation, doesn't it? Got some universal constant, 2 values divided by distance squared. It sure does. Right. Like universal gravitation. Okay. We'll be doing a little bit of circuits. Now the main things for circuits are you got like a voltage source, like a battery, for example, and resistors. Right? Those are the main ones. Okay. So these other ones are a little extra. Okay. We're good. All right. So real simple example. Here could be a flashlight. Right, so you turn on the switch that closes the circuit. Right, now the electricity can flow. Right, turn the bulb on. Right, a light bulb's the type of resistor, right, like that. Right now, how much electricity is going to flow? Right, that's Ohm's law. So if you know the battery is like 1.5 volts, that's what a AA battery is. It's 1.5 volts. There's also other kinds of batteries. It's like a 9-volt battery. If you know your cell phone charger is 5 volts. If you know the resistor, so whatever bulb you put on it, you can figure out how much current's going to flow in amps. So here's battery, chemical battery, what's going on there. Here's Ohm's law analogy. Electricity flowing through water, electricity through a wire is kind of like water flowing through a pipe. Make this analogy. Okay. I got this multimeter. There's a voltmeter and an ammeter setting in this. Again, I wanted to solve with you guys one day, well, maybe a couple days, but voltmeter measuring a potential difference. That's why you have to wire it sort of like across the resistor like this. Okay? But the ammeter, you're measuring how much current flows through the wire. So you guys notice that you have to like break open the circuit and force it to flow through the ammeter. So it's a little bit different setup. Right? How do you measure each one of those? Okay. We're looking at. I got some breadboards here. Got it here. Actually, I'll fire this up for you guys real fast. So here, guys, electric socket. Do you want to go plug in plug in like a pin in this electric socket right here?
No.
How about no? The answer was no. Yeah, things you learned in school. So that's 120 volts right there. It's in the States. But if I plug in the cell phone charger, it's going to jump this down to 5 volts. All right, now these open leads on the cell phone charger. Can I touch these leads? That 5 volts. Is that okay? 5 volts DC? Yeah, that's it. That's it, right? Let's see. Now the spreadboard, if you flip it over, look on the, well, mine has a tape on the back, but if you took this off, this is what it would look like. You can see these metal strips. So you see how it connects in here. And so anyway, I got a resistor here, got a couple of LEDs. Now remember, is it this way? It only flows one way. No, it must have been the other way. Try it the other way. Okay. LEDs, the electricity can only go through one way. They're polarized. So it's gotta be. Aha, there it is. Aha, look at that. You guys see it lit up? All right, create a basic circuit. Got some Christmas lights. I'll probably, yeah, I'd like to fit in a Christmas light lab with you guys one day if I can. Yeah, all right, so maybe one day. Get a real fast rundown today. Let's think out here. It expands on these resistors. You can read like how much resistance is that? Little colored bands here. This guy right here. All right. Show you guys Jules Law. All right, so that's a quick rundown of what my other classes are starting on today and want to do with you guys one day. Ooh, resistors in series, resistors in parallel, a lot of stuff, All right, a lot of stuff on your cop rules. All right, a lot of stuff for electricity. All right, but let's look at this energy packet. Energy packet. Okay, so I gave you guys one of these last semester. Well, this one actually updated a little bit, so it's got a little bit of updates. But see if you guys get this. So I've got all these different scenarios, and actually, no, sorry. Right before we get to the packet, let's do a little review on electricity, or sorry, energy. Okay. So make sure you guys can get these. Okay. Guys, what's the formula for work? Work is what times what? Force times distance. Guys, if you put a force on something for some distance, you're transferring energy into it. And also, guys, that's a dot product. The dot product means the force and the distance have to be in the same what? Same direction. Same direction. Right? Here, guys, for example, guys, if I lift this straight up, am I doing work to lift it? Yeah. So I'm giving it potential energy by lifting it, right? Okay. What if I carry this across the room? Am I doing any work carrying it across the room? No, because it's an upward force, but it's a horizontal movement. That has a zero dot product, right? Okay, so there's no energy transfer. Okay. Guys, what's the formula for gravitational potential energy? MGH. Yeah, MGH. Okay. In fact, if you lift it some force, it probably takes an mg to lift it, some height h, that'd be the distance. Hey, look at that. I'm getting it mgh worth of potential energy, right? Same thing. Okay. Now, this is actually a simplified version of, because what if you change your height so much that the gravity field actually changes? Then you can't really use MGH quite anymore, right? Like if you go from the Earth to the moon, right? You have to use what form of potential energy? Yeah, it's negative. It's GMM over R, right? Right. And if you picked 2 points, like if you went from sea level to the top of Mount Everest, and you found the difference of 2 negative GMM over R, it would simplify to MGH. I have a whole poster just for that too. Okay. How about, guys, here, let's talk about springs. Now, if you're putting a force on a spring, the force is equal to what? F equals Kx. And the energy stored in that spring, which is a different concept, is what? Guys, did everybody get that? Did everybody write that down in their notes? Here, I'll write it down with you guys. So you guys just said the force in a spring is Kx. Some textbooks throw a negative if you're talking about the restoring force. And the energy stored in the spring is 1/2 Kx squared. Right? Actually, let's make a little graph right here. If I made a force versus distance graph, this could be in newtons, this could be in meters. Okay? And say if you're compressing a spring or stretching a spring, one way or the other. Okay? The more you stretch or compress it, the more force it takes to do that. So, guys, what's the slope of this line equal to? K. Yeah, that's the spring constant. Okay. the more you press at X, the more force it takes, or the more it pushes back. If you're talking about restoring force, if you throw a negative. Okay. Yeah. That's what law? Hooke's law. Hooke's law. Okay. And guys, look right here. Guys, put your phones away, guys. Okay. The energy in the spring, or the work done to compress it, which is the same amount of energy, okay, is what property of that graph? Yeah, the area of the curve. If you find that the area of that triangle right there I just hatched in, that's also 1/2 kx squared as a formula, isn't it? Same thing. All right. All right. How about okay, so you guys got that. Okay. What's the energy of motion? Kinetic energy. 1/2 mv squared. Okay. Now, if you have a ball that's rolling, it almost looks like that. It looks like what? Aha, 1/2 I omega squared. Ah, sort of analogous, just in a rotating sense. Okay. Right, you guys remember all those? All those? Okay. Right, so you have to use a bunch of those. Oh yeah. Oh, why is the x squared? Yeah, let's take a look. Right, so we'll do a f versus x graph. Okay. Oh, I know if the slope is k, then this value up here is kx, right? As in f equals kx, right? So then like what's this area, right? Okay. Well, the area of a triangle, area is 1/2 base height, right? 1/2 base height. Okay. And the area in this case refers to energy, so I'll do U for energy in the spring. 1/2. The base is some value x, and the height is some value kx, right? Okay, put it all together. 1/2. There's a k. X gives you x squared. Okay. All right. Okay. So got that. Oh, guys, you're going to see this graph on the AP exam. You guys know you're going to see the set of axes probably multiple times, right? F versus x. And if you see F versus x, there's a good chance you're going to be asked a work or energy question, and that would be the area under the curve. Okay. So if it's a constant force for some distance, that would be a rectangle shape. But you might get a triangle shape, you might get some other weird shape. Okay. Okay. Ooh, next one. How about? Oh, I got an elevator set up. I'm gonna ask you guys about power. Guys, power is as a fraction is what over what? Work over time. There you go. Right, so it's like a rate of energy transfer, work over time. Now, work is equal to what times what again? Force times distance. Okay, so do that. Okay. And then you can group this together a little bit different. Guys, what is distance over time? Velocity. Aha. Force times velocity. So if this elevator is going up at constant velocity, do you think there's maybe a motor at the top of the elevator shaft pulling it up? Okay. Take some amount of power. Take some number of. How do you measure power? What's the unit for power? Watts. Ah, watts. Yeah. All right. All right. So it's a quick review right there. All right, think you guys are ready for these then. And so first scenario, Galileo drops the ball from leaning tower. So guys, tell me what's probably going to be in the closed system. The ball and the Earth. Yeah, there you go. There's the important things. Okay. Because if you did not include the Earth, then wouldn't Earth's gravitational force on the ball be an external force? That would no longer be a closed system. That would be an open system. So if you want to make it a closed system, you have to include the Earth. And that goes hand in hand with you're allowed to consider gravitational potential energy. Okay. Guys, what type of energy at point A? Gravitational potential energy. And what's the formula for that again? mgh. Yeah. Got a little subscript A there, maybe. Okay. And then at point B, let's say it's like a millimeter above the ground. It hasn't quite hit the ground. What type of energy at point B? Kinetic. And what's the formula for that? 1/2 mg squared. That would be at point B. Okay. Now, you guys know what the answer to this is going to be, what the speed at point B is, because you've seen this probably a couple dozen times, at least in this class. What's the answer to this question every time? Square root 2gh. Okay. Now, of course, you could get that by setting this equal to this. The mass of the ball cancels, and you can solve for v and always get that solution, right? Here, I got a twist on that question for you guys. What if Galileo doesn't drop the ball? What if Galileo throws the ball? Let's do that. Let's do Galileo throws the ball downward. I'll give you guys multiple choice what you think the answer is going to be. Option A, option B. Do you think the speed at the bottom is going to be? I'll give you two options. Is it going to be his throwing speed plus square root 2gh? Or is it going to be the square root of throwing speed squared plus 2gh? Okay. Let me see. Show of hands. How many guys remember this? How many guys think the answer? First of all, does anybody have a question about the question? Does everybody know the premise? So Galileo is at the top of the tower. He's going to throw a ball straight down at some speed VA. Right? And I want to know how fast is the ball crash landing on the ground. And it's one of these, but it can't be both because those are different things. It's one of those. Okay? Which one is it? How many guys think the answer is A? Who thinks it's option A? Who thinks it's option B? Who says option B? Ooh, there's my winners right there. It is B. It is B. Right. Now let's do this from scratch. This is about half and half. It's all about half and half. Okay. So let's do sum of energy at point A equals sum of energy at point B. Okay. Now, if you're throwing the ball downward, can you guys set up that full equation? Go ahead. Great. What's the next line right there? Go ahead. Set up the next line. You guys got that line? All right. What do you guys write for the energy at point A? Yeah, mgh at point A, plus also 1/2 mv squared at point A. And this VA is the throwing speed. That's how fast he was throwing the ball straight down. Okay. Now, by the time you get to point B, which is, again, a millimeter above the ground, what do you write for here? Yeah, 1/2 mv squared. But this is a different speed. This is the speed that's about to crash land. Guys, which speed is bigger, VA or VB? VB. It's got to be VB. Going faster there. It's picking up speed all the way along. Okay. Let's solve for that. Ooh, how many terms do I have? Three terms. Do they have anything in common? I can cancel out right here. Yep. The mass of the ball never mattered. Right, so it doesn't matter. Are you throwing this down? Are you throwing this down? The answer is going to be the same for the speed. Okay. Can I cross multiply this 2 right here? But it has to apply to both of these terms, right? So would that look like 2gh plus, and then this 2 and 1/2 cancels, so you just get VA squared. Right, and that's VB squared. Like that, right? So sure. You guys good? Hear that? Cross multiply the 2. Okay. And then what's the last algebra step? Square root. Square root. Yeah. So VB equals. So I need a giant square root. I got this VA squared underneath the root, and then plus. Now the square and the square root do not cancel because it's plus instead of multiply. If this was a multiply, you could cancel the square and the square root, but it's plus, so you have to treat it as different. 2gh at point A. So there you go. Right. Right, you guys go. Yep. Oh yeah, you're right. It is. It sure is. Yeah, you guys catch that? It's the same thing as this one right here too, isn't it? Same thing. Yeah. Good call. Cannon fires cannonball. Let's say at point A, cannonball is just left the cannon barrel. First of all, what's in the closed system? The what and the what? Yeah, the cannonball and the earth again. Okay. Now I'm leaving the cannon out because that's in the past, right? So the cannon has already fired the cannonball. That happened in the past. Right? At point A, the cannonball is already on the move. Right, so what kind of energy at point A? Yeah, it's all kinetic, 1/2 mv squared at point A. Okay. But I'm gonna call it basically height 0. So that's all. Right. Now at point B, what type of energy? Yeah, it's been lifted height B, so it has some MGHB potential energy, and it's also moving. Right? It's moving maybe horizontally. So there's also some 1/2 mv squared going on also. That's a point B. These B's are different. So now I've got three energy terms. So this is equal to this plus this. Right. Oh, yeah.
So we're just comparing, we were adding together both vertical and horizontal velocity.
Yeah, because guys, energy is energy a scalar or a vector? Energy is a scalar, which means that it doesn't really matter what direction these are moving. There's some total quantity of energy, kind of like some volume of liquid or something. It's the same idea as a scalar. Yeah. So if you start off with like 100 joules here, let's throw some numbers at it. All right. Let's take this one right here. I'll give you guys mass of the ball is like let's do 1 kilogram. It's going to cancel anyway, right? Let's say the firing speed was 100 meters per second. Let's give you Earth gravity is about 10 meters per second squared. And let's say the height change. So the height to get to point B. Now, let's call it 20 meters. Let's throw a number at it. Okay. And I want to know how fast is it going at that point. Now, notice that this is actually a little bit ambiguous. Notice I never gave you the firing angle. Do you guys see that? It turns out it doesn't matter as long as it reaches this 20-meter height. Right? If you fire it like straight up, you can fire this straight up and you can figure out how fast it's going at 20 meters. Or you can fire it at a shallow angle where it just barely gets to that height and maybe it's going horizontal at that point. Okay? And the answer is going to be the same, how fast it's moving at that particular height. Okay. So go ahead. You guys solve it. I'll solve it. Let's see if we get the same answer. You solve it. I'll solve it. Ooh. All right. I got the answer. How about you guys? Yeah. Who knows the answer? What you got?
Square root b squared a.
Yeah. How about it as a number? As a number.
Oh, sorry.
Looking for. All right. I got a number on my calculator screen. Oh, somebody tell me what number is on my calculator screen. Huh? Yeah. Faster. Well, guys, if the cannonball is kind of going upish, it's going to be speeding up or slowing down. Guys, is the cannonball ever going to be going faster than 100 meters per second? No. Yeah, there you go. All right. Hector got it. I got it. Actually, I think I picked kind of a ridiculous number because this is a really fast firing speed, and this is probably not very high. I got the same thing Hector got, which is about 98 meters per second. Okay. So here, let's run the numbers. So here's your setup right here. So do sum of energy at point A equals sum of energy at point B. Okay. At point A, it's all 1/2 mv squared at point A. And at point B, that's some mgh plus 1/2 mv squared. Like that. Set here. Okay. Now, if I plug these numbers in, do a little shortcut here. Because I told you, all right, let's just do 1/2 mass of 1 kilogram. The speed was 100 meters per second, and I have to square that. That's like 5,000 joules. I got 5,000 joules in the system. Okay. Right, sure. Okay. And that's equal to. Okay. Now, some of that energy goes into lifting it against gravity. Probably not very much. Let's do 1 times 10 times 20. Yeah, only 200 joules actually go to lifting it. Therefore, what is the energy left over? Yeah, it has to be 4,800. I know I'm solving this a little bit weird. That's a little bit different. You could just plug the numbers in and solve it with algebra, but a little bit different point of view. Is that okay? Do you guys see how the energy has to equate like that? Okay. So I know that this 1/2 mv squared has to come out to 4,800 joules. If I plug in all the numbers, subtract this over, blah, blah, blah. Okay. So how do you undo this? Well, 4,800 joules equals 1/2. 1 kilogram is the ball. And then we're solving for how fast it's going. Now it's being squared here. So gotta take the square root there. So I have to multiply by 2 and take the square root. Is that right? Times 2 square root. So 4,800 times 2, right? Gives me 9,600. And I have to take the square root. The speed at point B is, about 98 meters per second. You go. That's it. All right. Oh. Now, guys, these next two examples are the only open systems I have in this whole packet. Everything else is closed systems, right? So let's consider, okay, I got a kid in a sled and he's sliding down the hill and there's friction. Let's consider the kid in the sled. And maybe you could also throw in the earth. Whether you do or not, it's still an open system. Because there's also a friction force from the hill, okay? So that would be an external force. Guys, what kind of energy at point A? Yeah, potential energy, MGH. Okay. Now, in the circle, now this is an updated version. This is one of the updates from a few minutes ago. Okay. Since this is an open system, you have to consider an energy change. This is going to be work done by friction. Guys, is work done by friction going to be positive or negative? Negative, because it's taking energy sort of out of the system. Right? And what is the formula for work for some force and some distance? Force times distance. So subtract off the friction force times this length L is the distance that it acts over, right? Friction force times L. Okay. Now you could get more specific. You could say, guys, what's the formula for friction force equal to what times what? Coefficient of friction times normal force. And the normal force on an incline is equal to mg what? Cosine. Mg cosine theta. You guys remember all that? Right. So if you were told the coefficient of friction and you were told the angle, you could go more specific with that friction force right there. You could do that, right? Okay. And then let's say by the time he gets to point B, he is still in motion, but he has no height basically. But he's still in motion. He has what kind of energy at the bottom? 1/2 mg squared at the bottom. Right. And you say this minus this is equal to this, right? This minus this is equal to this. Okay. So maybe a little equal right there. This minus this equals this. Okay. Let's do a car break into a stop. Let's consider a system of only the car, which again means it's an open system because there's an external force, which is the force from the road, right? The friction force from the road. Right? Now you could say, well, okay, I guess the Earth's pulling down on the car also, but that's just canceled out by the normal force. So, okay, it didn't really change it. Okay. So, what kind of energy at point A? Kinetic, 1/2 mv squared. Now I have to subtract what times what? Friction force times sliding distance. Right? Because again, it has to also be an energy term, right? Work as an energy term. Right? So this much energy, this many joules minus this many joules leaves you with
0.
Yeah, you're right, 0 joules at the very end. Actually, I do have a poster just for that. Please see if I can dig this up real fast. How's this? Where's my car break into? Here's my car break into a stop. Oh yeah. There's a whole poster just for that one right there, isn't it? Is that what we just did? Okay. Right. And then like I was just saying a couple minutes back, you could take this friction force, you could say, well, it's coefficient of friction times normal force. Now, normal force in this case would be equal to the weight, because it's all just a flat road. Okay? And you can solve for the braking distance as one of the classic physics questions. And this always ends up being the solution to that question. Okay? And then also very often, a question that I like to ask, I've seen asked a lot all over the place is, what's the relationship between the braking distance and the initial speed? Because if you triple the initial speed, what happens to the braking distance? 9 times. Guys, 3 times the speed is 9 times the braking distance. That's this here, which is this here. Isn't that here? Right, right there. Okay. Got that. All right. So you guys good with these 4 so far? All right. 2 closed, 2 open, and the rest of these are all closed systems. Okay. Ooh. I'm going to put 3 objects in this next system. The what, and the what. Let's go. Yeah, the block, the spring, and wait, did I hear the third one? The earth. Yeah. Block, spring, earth. Okay. Now, the reason that you don't actually have to include the track itself is because, guys, is there a track? Is there a force from the track acting on the block?
No,
Hold on. Yeah, the normal force, right? But here's the catch: the normal force is always oriented how compared to the motion of the block? perpendicular. And if the force and the motion are perpendicular, is there ever any energy transfer from that?
No.
No. So the normal force never actually does any work on the block. That's why you don't actually have to consider it. Right? And oh yeah, also the fact that it's frictionless. Right? So for both those reasons. Right? What type of energy at point A do you think?
1/2 kx squared.
Aha, 1/2 kx squared, which is your spring potential. Aha. Okay. Now, by the time it gets to point P, what point B? Pew! Well, it's been lifted against gravity. It better also be in motion, otherwise it wouldn't have made it through that loop, right? So, what kind of energy here? You got some mgh at point B, and also what? Yeah, also some 1/2 mv squared at point B. Right. So, if this is like 100 joules, maybe this is 30 joules and 70 joules. No, I can throw numbers at you guys. I can tell you how stiff is the spring. I can tell you how much you compressed it. I can give you the mass of the block and all these other numbers. Could you guys solve for the speed at point B if I gave you a bunch of numbers? Do that? Yeah. Yeah, right. Great. Good so far. Very good so far. Right. All right, how about, actually this next one I kind of stole from a past free response question. Actually, this is a simplified version. I got a bungee jumper here. So what type of energy at point A? Or here, actually, what's in the system? Yeah, the bungee jumper and the earth, and also the what? Yeah, also the cord, the bungee cord. Now at point A, there's definitely what kind of energy? Yeah, potential energy, mgh. Okay. Now, there might be more energy depending on how you interpret this. See where I said where he dives off? Okay. Now, if he just steps off the platform, then that it's just mgh. That's all. Right? But what if he does a running jump? If he does a running jump, there's also what? Yeah, so there might also be 1/2 mv squared, depending on how the question is worded. It'll put that in parentheses. Okay. Let's say at point B, the cord stretches and he just barely touches the ground and then it retracts. So at point B, where'd all the energy go? It's all in the spring. And that's what kind of energy? 1/2 kx squared. Aha. Where x is how much the cord stretched beyond its original length. Actually, I think I made one for this one too. Yeah, there we go. Made a poster just for this one. I found it. All right, so it'll be like this. Right. So if the cord unstretches length L and stretches length X, then isn't L plus X the entire original height?
Yeah.
Okay, you guys see that? Okay. And then remember in the past, AP took actually okay, guys. All right. The question that I stole this from, there was additionally some height above the ground. So you had to also consider that the gravitational potential at the end had an extra mgh. Okay, but otherwise it'd be the same stuff. Okay. So AP's asked that pretty much in the past. Okay. How about I got a couple of outputs here. Let's do the classic output first. Classic output. So I have to consider M1, M2, and also what? The Earth. Aha. M1, M2, and the Earth. Actually, I think it's true for both of these. M1, M2, Earth. Okay. Oh. Now, it looks like what's going to happen is M2 is going to fall down, which is going to lift M1. So now there might be more than one way to set this up. But here, brought you guys kind of one way. The fact that M2 is going to fall means it's providing what type of energy? Potential energy, M2UGH. That's sort of the source of the energy. That's like the impetus for it to move. The fact that M1 is so large and it's elevated and it's going to fall down. Okay. Hey guys, by the time it gets to point B, so both these blocks are moving, right? Okay. What type of energy at point B? Aha. Here, you guys finish that equation. So M2GH equals, go ahead and write the full equation. Hey, take a quick trip around the room, make sure you guys are writing this right.
Which food are you talking about? Yeah, okay, so I don't know that. On the cafeteria, dining hall, dining.
Okay. All right, so what you guys come up with is, he said it has to lift M1. So some of the energy goes into lifting M1. Okay. M1GH. Okay. Also, at the end of that motion, aren't both blocks still moving? And that's what kind of energy? Yeah, 1/2 MV squared for block one, and also 1/2 MV squared for block two. Okay? Now, do I have to consider, wait a minute, one block is going up and one's going down. So are these both plus? I'm gonna say they're both plus. They're both plus. Yeah, they're both plus. Because energy is a what? A vector or a scalar? It's a scalar. Right? It doesn't matter the direction of motion of these blocks for this particular technique. Right? Now, I think the same thing was true on this cannon back here, right? You guys remember this cannon? But we don't actually know the direction the cannonball was fired. See, if I gave you the angle, if I told you, oh, this was 35 degrees or something, you could use projectile motion and probably also get to the same answer, right? But I didn't tell you anything, right? So, yeah, you don't actually care the direction of motion. You just care the fact they have some kind of speed. Right. All right, you guys go with that? All right, how about the modified one? Oh, what do you think you're gonna do for energy at point A? Yeah. So M2G. Oh, looks like I call this X. Whoops, I meant to change that. Whatever. X. He's gonna fall some distance X. Okay. And then by the time you get to point B, where'd all the energy go?
Kinetic energy in both blocks.
Aha! Kinetic energy in both blocks. 1/2 MV squared plus another 1/2 MV squared. But the M's are different because it's two different blocks. So back again, that up. Right, is that okay? Right. And yeah, I got those right here. Right. So here's the classic and the modified Atwood setups. Right. So here's the classic that we just did a minute back. Right. So large block falling, lists a small block and gets what we just beat. Right. So potential kinetic energy. Okay. And then here's the one we just did right now. Right. This block falling, and this block might be the small block, but it doesn't matter because one's gonna fall. Right. And it's gonna give each block motion, kinetic energy connected. Right. It's got some number of joules, some number of joules, some number of joules. Okay. Guys, can you add an energy term to a force term? No, you can only add energies to energies. And you can only add forces to forces. All right, everybody gets a far, gets a far. Of course, you guys can solve for the speed of point B. Any of those happy? Okay. Ooh, these next two look pretty similar. I got a spring firing a ball, and then the one after that, the ball falls onto the spring. So what do you want to consider in the system? The ball, the earth, and the spring. What kind of energy at point A for this one?
1/2 kx squared.
Yeah, spring energy, 1/2 kx squared. And then at point B, at the maximum height, it's all what type? MGH. Okay. Now for this next one, which I think is the same system, what type of energy at point A? MGH. And at point B, 1/2 kx squared. Okay. Now you are doing the simplifying assumption. I know there's a collision there. Whenever you see a collision, you should think momentum, with the exception of if there's a spring and it says to ignore the fact that it's a collision. They might say like a negligible mass spring. All right, now these last two, a little trickier because, ooh, we got some rotational dynamics for this one. Guys, this ball rolling downhill. Let's consider the ball, the earth. I'm going to also throw the incline in it because there is a frictional force, but it's not actually taking energy out of the system. It's just inducing a torque that's inducing rolling. Okay. So what type of energy at point A? MGH. Now at point B, what forms of energy?
Kinetic energy, and then you have rotational.
So there's translational kinetic, 1/2 MV squared. And there's also rotational kinetic, 1/2 I omega squared. Right? There's a little bit of both of those. Okay. Now, guys, is this I related to this M?
Yeah.
Yeah, because if this was like a solid ball, like a bowling ball, I could call this 2/5 mr squared, right? But you could find that rotational inertia table. And is this omega related to this V?
Yeah.
Yeah, that's also true, isn't it? Omega is equal to V divided by R, or V is equal to omega times R. You know, either way, depending on what you're solving for. I'll give that hint right here. Okay. All right, and all right, so is that okay? Okay. Now, you guys know if this is a basketball versus a bowling ball versus if this is rolling out, it's a solid cylinder rolling down. These would all have different I values, right? Yeah. Something mr squared be 2/5, 2/3, 1/2, something like that. Yeah. And then last one here. Now this one's also a little bit tricky. I got two asteroids that are gravitationally attracting, and they're going to move some distance. But let's consider that the gravity field would also significantly change. So it's not a constant gravity field. So let's say each asteroid. So we'll consider that basically a closed system, just the two asteroid system. What type of energy at point A? Negative G M over R at point A. Okay. Now, when they gravitate closer together, oh, and let's say they start from rest. Yeah, it says start from rest. So that's all. When they get closer together, is that negative G M over RB? Is that what that would be? Okay. Now, since RB is a smaller number than RA because they're closer together, if I ignore the negative for a moment,
There's still energy.
yeah, isn't this like a larger fraction?
Yeah.
But then if you consider this negative, it's a larger negative number. So it's like if you go from negative 10 joules to negative 20 joules, right? You guys see that? Okay. So those extra 10 joules have to go somewhere. They all went to motion. Isn't that plus 1/2 mv squared plus another 1/2 mv squared? Right? So you may have like negative 10 joules equals negative 20 joules plus 5 joules plus 5 joules, for example. And just okay. I can give you some numbers so you can plug it in and solve for it. Okay. All right, is that okay? All right. That's a pretty good pause point today.
Alright.